Hello everyone, in this video I'm going to be talking about intermolecular forces. Personally, intermolecular forces is one of my favorite topics in chemistry because it tells us everything about the physical properties of different molecules, whether something's going to be a liquid, a solid, a gas, aqueous, a salt, etc. That is all determined by intermolecular forces, right? So what intermolecular forces are, they are forces between molecules, right? So I have a little picture here depicting this. Don't mind like the arrows, just focus on your hydrogen, your water molecules. Sorry. So just focusing on your water molecules. I'll talk about this a little bit later, but what we say is that one hydrogen is, or both hydrogens are slightly positive and the oxygen is slightly negative. So what's going to happen is kind of going to work like a magnet, right? They're going to be attracting each other. Now, this thing doesn't have a positive charge itself, right? It's not a cation, and the oxygen is not an anion in this scenario. They're just slightly positive. And that's because all the electrons are kind of going to this. So this doesn't become an anion, and that doesn't become a cation, but there is a slightly negative and a slightly positive portion on those water molecules, so they can be attracted to each other. So that's kind of how those intermolecular forces work, right? They're not bonding together, they're just kind of acting as a magnet, as you could kind of say. So there's 4 different types of intermolecular forces, and that's ionic dipole, hydrogen bonding, dipole-dipole, and London dispersion forces. There's some other factors that affect your intermolecular forces, and that is your mass and temperature. As the mass increases, the intermolecular forces will also increase, and that can kind of just be thought about. I don't know. For me, that just kind of like makes sense, right? You think about air, very light. It's a gas, right? So it has to be really, really light to be able to float around and act as a gas. Versus something that's solid, it usually has a lot of weight to it, right? When you're comparing like the moles versus mass, right? The heavier something is, the more likely it is going to be having a stronger intermolecular force, aka being a solid or a liquid, versus something that doesn't weigh a lot, it's more likely to act as a gas. The next thing is temperature, and as the temperature goes up, the intermolecular forces go down. Going back to water, we can think of this as when water is melting and water is freezing. As the temperature is going up, let's say that you're boiling water, you're actually causing those molecules to bounce around because they're gaining more energy. So they're going to bounce around, keep bouncing around. Because of that, they are less likely to be attracted to each other because they have so much energy that they're just moving all around and they don't really get too much of a moment to be attracted to each other, if that makes sense, right? So let's say, I don't know. Yeah, I hope that like makes sense. I would do like a theoretical thing, but that would probably make it more confusing, so I'm not going to. But then let's think about when we bring the temperature down. When we bring the temperature down, these molecules are going to be less excited. So they're actually going to have more of an opportunity to have a moment where they can be attracted to each other, right? So that means that they are more likely to become a solid or a liquid when the temperature is lower. So therefore, as temperature goes up, the intermolecular forces will go down. Okay, so let's take a look at ionic dipole. So ionic dipoles are only present in things that are ionic molecules. So it's always going to be a metal and a non-metal, right? So this usually creates a salt, and we know that because, well, here's actually table salt, but there's other things out there like CaCl. I'm sure we've seen so many of these already. KF, that would be one. K would be your metal, F would be your non-metal, but let's take a look at sodium chloride, good old table salt. The Na is a cation, so it's positive ion, and we have Cl, which is a negative ion, aka an anion. So you have your metal and your non-metal. They're going to come together. The chlorine is going to donate an electron to sodium, so they're going to have an extremely strong bond together. And because of this, they are very, very, very strong intermolecular forces. They have an extremely high melting point and an extremely high boiling point, almost to the point where it's nearly impossible to melt them. We actually did an experiment in, I think it was AP chemistry, where we were tasked with melting salt, which you can't really do in order to, like, state whether something has an ionic dipole or not, right? If it melted, it was likely not having an ionic dipole, but it's really, really, really hard to melt something like salt, like table salt. And that's just because their intermolecular forces are so strong that it takes so much energy to break those intermolecular forces. So that's that. Let's move on and take a look at hydrogen bonding, which is the second strongest intermolecular force that we will be looking at. Hydrogen bonding is like my favorite because it's probably one of the coolest, I guess, in a way. This and London dispersion are definitely my favorites, but either way. Hydrogen bonding is only when hydrogen is bonded to oxygen, nitrogen, or fluorine. And the reason why it's only during those types of bonds is because oxygen and hydrogen, nitrogen and hydrogen, and fluorine and hydrogen are very polar. I don't know if you guys remember when we were taking the last test, we were actually talking about how hydrogen has the lowest has the highest electronegativity. And then or does it have the lowest? I don't exactly remember, but hydrogen is either the highest or the lowest. I don't exactly remember. I want to say it's the lowest, but yeah, that would make sense. Hydrogen probably is the lowest, but either way, when you have something that is also electronegative, it's going to make a very polar bond, right? And because the bond is so polar, it leads to a very uneven sharing of electrons. So let's take a look at our water molecule here. So we have a water molecule. As I was saying before, you have slightly positive, and slightly negative. Let me actually try to do this. See if I can do this right. So let's try to draw out what the electron cloud would look like, right? So this is going to be slightly negative, and it's going to be, the oxygen is actually pushing all the electrons towards it because it's so negative. That this is kind of what the electron cloud looks like, right? So very uneven sharing of electrons. And because of that, it's going to be very polar, right? It's going to be more polar than your regular old polar molecule. It's like extremely polar. And because of that, it's going to cause a high boiling point, a high melting point, and overall it's going to have very, very, very strong intermolecular forces. So that's why hydrogen bonding is so special. It's just because you have two things that are so different in electronegativity that they're just so extremely polar that not even polar molecules are really close to it. So yeah, that's kind of why that one's special and why it's the second strongest. So now let's take a look at dipole-dipole. So with dipole-dipole, they must be polar, but not hydrogen bonding, right? So let's take a look at our polar molecule here. We have CH3F, right? So we remember that something that's polar is usually going to be any molecule with an uneven sharing of electrons, right? Fluorine is more electronegative than hydrogens, so fluorine is going to attract more of the electrons, and there's going to be an uneven sharing of electrons. Very similar to our last slide where we were talking about the uneven sharing between oxygen and hydrogen, but it's a little bit less of an uneven sharing, but they're still polar. Like, this is still going to be slightly, let me write it out. This is still going to be slightly negative, and up here is going to be slightly positive, but it's a lot less than the hydrogen bonding, right? So that's why this is going to be your third strongest, just because, same thing as before, right? This is going to act as kind of like a magnet, and it's going to attract the slightly positive side of another molecule, and so they're going to be a little bit more tight together and more attracted to each other. These are usually going to be your volatile liquids, right? So when we say volatile, I'll make like another video kind of explaining, or actually I'll just explain it now. Volatile is basically the ease of evaporation. Oh god, I totally spelled that so wrong. But volatile is basically the ease of evaporation, and if you think about something like, let's see, what's something that's volatile that's not hydrogen bonding? I'm trying to think of one. Acetone might be one. Let me just look up the acetone molecule. Okay, so yeah, acetone. Looks like this. It's very polar because you have that oxygen there that's going to actually be pulling at the electrons. And for any guy out there who has not gotten their nails done, when you have acetone on your hand, the acetone evaporates very easily, right? Like you could probably, I actually have acetone right next to me, but if I dumped this entire bottle of acetone in my hand, it would probably be gone in like less than a minute. And for anybody there who has, or anybody here who has used acetone on like their hands to get nail polish off, you notice that your hand gets cold because it's actually evaporating and using the heat from your finger or your hand to evaporate, right? So volatile is basically just the ease of evaporation. And as the volatility goes up, the ease of evaporation of evap goes up. So we could say that acetone is very volatile, alcohol very volatile. Yeah, but those are going to be your volatile liquids basically. And this is your third strongest, as I said before, because of the fact that there's still that slightly negative and slightly positive. Okay, so the last intermolecular force that we're going to talk about is our London dispersion forces. So London dispersion forces are really cool. They're kind of a hard concept to understand because it's not like right in front of your face, like, oh, here's exactly what's happening, right? When you're looking at a polar molecule, it's kind of easy to be like, okay, well, uneven sharing of electrons, that's going to make something slightly negative and slightly positive. Cool, got it, good. With London dispersion forces, it's always going to be your non-polar, non-metal molecules, right? So that would be something like CH3. Oh, that's not a molecule. CH4. So it's something like CH4, right? It's going to look like this. There's no uneven sharing of electrons. All the electrons are being shared equally, and they're all non-metals, so that's going to be your London dispersion forces. The larger something is, the greater London dispersion forces, and the reason being is because it's caused by dipole moments in the electron cloud. You're probably like, what does that even mean, Grace? What is a dipole moment and what is an electron cloud? So, what an electron cloud is, I've talked about this before, but I'll review it a little bit. What an electron cloud is, it's basically the cloud of electrons around a molecule. So let's say that this is the electron cloud of this molecule, right? It's just kind of, this is around where we think the electrons are in this molecule. So we call it the electron cloud, right? What London dispersion forces do is that it actually, I have like a little video showing it, creates dipole moments where there's going to be a moment where this is going to be slightly negative and it's going to be slightly positive. So I'm going to show that video. I'm not sure if the sound is going to go through, but I'll talk about it. Yeah.
Temporary negative pole on the side become polar for very brief moments, since the locations of electrons around atoms are constantly changing. This means the molecule can have a temporary negative pole on the side where there are momentarily more electrons, and a temporary positive pole on the opposite side where there are fewer electrons. The momentary concentration of electrons in this molecule's negative pole can repel the electrons in a nearby molecule toward its opposite end, making the neighboring molecule polar as well.
Okay, so I'm not exactly sure if the sound came through, but what that video is basically showing is that electrons move around constantly. So let's say that this electron cloud at one moment is going to be over here, it might be over here. They're constantly just kind of shifting around. They're staying in a little bit of a general area. They're not going to go all the way over here, but they're kind of moving around. So let's say that the electron cloud is about right there. That is going to make, fix my little pen here. That is going to make this side slightly negative and this side slightly positive because the electrons are shifting towards this one side. So this one side is going to be slightly negative and then this side is going to be slightly positive. The reason why we call it a dipole moment is because this does not stay for long. As I said before, the molecule is constantly just kind of shifting around like this, and the electron cloud is just kind of bouncing around. So at one moment it might be here, one moment it might be here, might be there, but these little dipole moments creates those slightly positive and slightly negative charges, which again, same thing with what we just talked about. It kind of acts as a magnet, therefore attracting more molecules, right? So this is going to be your weakest intermolecular forces, and this is mainly present in your gases. So this is actually methane. Methane is a gas. It's actually the gas, I'm pretty sure, that like cows produce, which is really bad for the environment, but I don't know, don't at me on that. So yeah, it's mainly your gases and it's going to be your weakest. And then I also want to add a little note there that all molecules have London dispersion forces. And the reason being why all of them have London dispersion forces is because all of them have electron clouds, so all of them are capable of having dipole moments. Again, like hydrogen bonding, if you have something that's hydrogen, like has hydrogen bonding, that's going to be way stronger than the London dispersion forces, but the London dispersion forces are still there and they're still kind of contributing, but they're being a lot outweighed by the hydrogen bonding. So we don't really mention it, but if a question asks, what are the intermolecular forces of something that's hydrogen bonded, you could say hydrogen bonding and London dispersion forces, right? Because those both are present. Okay. So let's go into some practice problems. I hope this practice problem saved. It doesn't look like it did. Oh my goodness. That is not good. All right, so we'll just work through. I'll remake those ones when I get there. But let's work through these problems. So, which of these molecules has hydrogen bonding? So the first one is CH3. CN. So the first thing I'm going to do is I'm going to actually draw out the molecules. So we have, let me make this pen a little smaller. So we have C with 3 H's around it. And we have another C, and it's going to be bonded to a nitrogen. Okay, so right away I can tell that this doesn't have hydrogen bonding because of the fact that the nitrogen present doesn't have a hydrogen attached to it. So we're going to say no. All right, the next one is CH3CHNH. Okay, so C with 3 hydrogens around it. Then another C with 1 hydrogen on it, with a nitrogen with a hydrogen. Okay, so this has our nitrogen-hydrogen bond. So I'm going to circle that now. There might be more answers, but let's keep going through. And then our CH3, oxygen, CH3. Okay, so this oxygen is not bonded to a hydrogen, a nitrogen, or a fluorine, or is not bonded to an oxygen, wow, I'm losing it. The oxygen is not bonded to a hydrogen, so we can say that this does not have hydrogen bonding. And the next one's all. So all of them don't have hydrogen bonding. So this will be the only answer. Okay, so which of these molecules has London dispersion forces? All right, so this is actually what we just talked about. So as we said before, all molecules have London dispersion forces, even though that this one is simply just London dispersion forces. So we can say this one has London dispersion forces. This one is dipole-dipole, but we can also say that it has London dispersion forces. H2O is going to be hydrogen bonding, but it also has London dispersion forces, so the answer is going to be all. If you guys will be patient with me as I go and write some more of these questions, we'll do that. So let's do this, where we're going to list the molecules from highest intermolecular forces to lowest intermolecular forces. All right, so let's say we have A here, B, C, D, yeah, and then I'll do the same thing down here. List molecule from, we'll say highest boiling point to lowest boiling point. Oops. From highest boiling point to lowest boiling point. I'd like a little line there so you guys can write the answers. Okay, so we'll do C2H6, we'll do C4H10, C6H14, and then we'll do C8H18, I believe would be the amount. Okay, so the next one we'll just do NaCl, H2O, we'll do CH4, and we'll also do, what else could I do? HC3Cl. Alright, so apologies for that. Sometimes this program likes to just delete my things, so apologies for having to rewrite those problems, but let's list these molecules from highest intermolecular forces to lowest intermolecular forces. Okay, so the first one is that's supposed to be NaCl. Apologies for that. Okay, we're just gonna do it this way, I guess. Okay, this is NaCl now. So we have NaCl. NaCl is gonna probably be our first highest because that's our ionic bond. We'll say. And then H2O is going to be hydrogen bonding. Let's see if any of these others have hydrogen bonding. Okay, so this one doesn't have hydrogen bonding, so we're going to say this is going to be our second because of hydrogen bonding. And then C is only going to be London dispersion forces, so I'm assuming this is going to be number 4. And then this one is going to be dipole, because it's only polar, doesn't have any hydrogen bonding. So this will be our 3. Alright, so this will go, we'll just do A, B, highest to lowest. Okay, cool. Make sure I did it right. A, B, D, C. Okay, so now we're going to list these molecules from highest boiling point to lowest boiling point. So a high boiling point means that it has a high intermolecular force. So this first one here, well, let's actually just compare all of these at once, right? So these are all the same kind of molecule, they're all hydrocarbons. So the only thing that we can compare here, we're going to assume that these are all at the same temperature and pressure. So the only thing that we can compare here is the mass, right? And as we said before, as the mass increases, the intermolecular forces will also increase. So I'm going to say that this one has the highest. So this one will be the highest. This one's going to be second highest, third, and fourth. So it'll be D, C, B, A. Cool. So that's not it for this video. I have a little bit of a review. So it's just like a little bit of a review for the intermolecular forces. Oh my god, I literally spelled review wrong, I think. I don't know. It might be right. I don't know. But again, it's affected by temperature. As temperature goes up, intermolecular forces go down. As mass goes up, intermolecular forces goes up, and it's also affected by the types of forces. The highest one is ionic, then there's hydrogen bonding, then dipole-dipole, and London dispersion. So be sure to definitely take a look at these. YouTube videos are really helpful. Reading it up in the textbook is also very helpful because they have a lot of pictures showing how these things work. But thank you all for watching, and have a good one.